One of the most important aspects of the study of chemical reactions, other than predicting their feasibility and the extent to which they would proceed, is the time taken for their completion. That is, the rate of a chemical reaction. Let us understand this in detail. In our daily lives, we see various chemical reactions taking place. For example, the rusting of iron in the presence of humid air and the combustion of butane, the main component of LPG. While the rusting of iron is a very slow process and may take years, the burning of butane is instantaneous. There are some reactions which take place with a moderate speed. Photosynthesis is an example of a moderate reaction. Have you ever wondered why some reactions are slow while others are fast? Chemical kinetics is the part of physical chemistry that studies reaction rates and explains why certain reactions are instantaneous and others are not. It also describes the conditions by which reaction rates can be altered. Let us start with a simple definition of the rate of a chemical reaction. The term rate is often used to describe the change in a parameter that occurs per unit time. For example, the rate at which an aeroplane travels is the distance travelled per unit of time, such as kilometers per hour. In chemical kinetics, the rate of a chemical reaction is defined as the rate of decrease in the concentration of the reactant, or the rate of increase in the concentration of the product. Thus, the change in the concentration of the reactants or products with respect to time is called the rate of a reaction. In other words, the reaction rate or the rate of reaction specifies how fast a reaction takes place. Consider a simple reaction in which 1 mole of a reactant A produces 1 mole of product B. Let us assume that the volume of the system remains constant. Initially, that is, at the beginning of a reaction, the concentration of reactant A is maximum, while the concentration of product B is 0. As the reaction proceeds, the concentration of reactant A decreases, while the concentration of the product B increases. Let A1 and B1 be the concentrations of A and B respectively at time T1, and A2 and B2 be their concentrations at time T2. The decrease in the concentration of reactant A, delta A, during time interval delta T equal to T2 minus T1 is given as A2 minus A1. Similarly, the increase in the concentration of product B, delta B, is given as B2 minus B1 during time interval delta T. Using the definition of rate of chemical reaction, we get the rate of the given reaction as a decrease in the concentration of A minus delta A divided by time interval delta T. Now, delta A is a negative quantity since the concentration is decreasing with time. So we multiply it by -1 to make it a positive quantity, as the rate of a chemical reaction is always positive. Similarly, the rate of the given reaction is also given by the increase in the concentration of product B, delta B, divided by time interval delta T. In this case, delta B is a positive quantity since the concentration of the products always increases with time. Hence, we do not multiply the rate of reaction by a minus sign. However, the rate of reaction is not constant. It changes with time. The rate of disappearance of reactants gradually decreases with time as the reactants are consumed. And the rate of the appearance of products increases with time as the products are formed. Hence, the rate of reaction is always taken as the change in the concentration of the reactants or products in a definite interval of time. This is called the average rate of chemical reaction, which is given by this equation. If we plot the concentration of A and B against time, we get the graph shown here. From the graph, we can see that the concentration of reactant A decreases with time, while the concentration of product B increases with time. Note that the change in the concentration of the reactants and products and the time taken for that change to occur, as shown here, depicts the average rate. However, the average reaction rate doesn't predict the rate of reaction at a particular instant of time. To predict the rate of reaction at a particular moment of time, we take an infinitesimally small time period, dt. That is, when time delta t approaches 0, and measure the change in the concentration of the reactant or product during this infinitesimally small time period. The rate of a reaction determined at a particular instant of time is called the instantaneous reaction rate. If the changes in the concentration of A and B are dA and dB respectively, during the infinitesimally small time interval dt, then the instantaneous rate of reaction is given as R instant equal to minus dA by dt or equal to dB by dt. Graphically, we can determine the instant rate of chemical reaction at time t by drawing a tangent at time t on the curves for the concentration of either A or B, and then calculating its slope. The slope of a tangent gives the instantaneous rate of reaction at that particular time. The change on the y-axis divided by the change on the x-axis gives the slope of the tangent. From the graph, the slope of the tangent drawn gives the instantaneous rate. R instant equal to minus dA by dt equal to dB by dt. The rate of reaction may not be same with respect to all the reactants and products. It depends upon the stoichiometric coefficients of the reactants and the products in a balanced chemical equation. Let us consider the formation of hydrogen iodide from its constituents, hydrogen and iodine. The balanced equation for this reaction is shown here. In this case, 1 mole of hydrogen and 1 mole of iodine react to give 2 moles of hydrogen iodide. That is, the rate of disappearance of hydrogen is equal to the rate of disappearance of iodine, and the rate of disappearance of hydrogen or iodine is equal to half of the rate of the appearance of hydrogen iodide. Hence, the rate for this reaction can be written as shown. Let us now consider a generic reaction, where the stoichiometric coefficients of the reactants and the products are different. Let's say m moles of A react with n moles of B to give O moles of C and P moles of D. We divide the rate of appearance of the products and the rate of disappearance of the reactants by their respective stoichiometric coefficients to get the rate for the overall reaction. The rate of chemical reaction in this case is given as -1 by m into delta A by delta T equal to -1 by n into delta B by delta T is equal to 1 by O into delta C by delta T is equal to 1 by P into delta D by delta T. You have learnt about the rate of reaction. Let us now look at the units for the rate of a reaction. If the concentration is in mole per liter, then the unit for the rate of reaction is mole per liter per second. For gaseous reactions, if the rate is expressed in terms of their partial pressures, that is, the rate of change in partial pressure of the reactant or the product, then the unit for the rate of reaction is atmosphere per second. You have already learned that the rate of a reaction decreases with a decrease in the concentration of the reactants. Thus, one of the factors that determine the rate of a reaction is the concentration of the reactants. The representation of the rate of a reaction in terms of the concentration of its reactants is known as the rate law. It is also called the rate equation or rate expression. It is important to note that we can determine the reaction rate in terms of the concentration of the reactants only by experimentally, and it cannot be determined from the balanced equation. Consider the reaction given here. Let's say m moles of A react with n moles of B to give O moles of C and P moles of D. We can write the rate law for this reaction as rate of reaction is directly proportional to the concentration of A raised to the power x multiplied by the concentration of B raised to the power y. By replacing the proportionality with proportionality constant K, the equation can be written as shown. The K in this equation represents the rate constant. The exponents x and y may or may not be equal to the stoichiometric coefficients m and n of the reactants A and B, respectively. This expression, which relates the rate and concentration of the reactants, is called the rate law or rate expression. Thus, rate law is the expression in which the rate of reaction is given in terms of the molar concentrations of the reactants, with each concentration being raised to some power that may or may not be the same as the stoichiometric coefficients of the reacting species in a balanced chemical equation. You know that the rate of a reaction with respect to the reactants is equal to minus dr by dt. Therefore, the equation can be written as minus dr by dt is equal to K multiplied by concentration of A raised to the power x multiplied by the concentration of B raised to the power y. This is known as a differential rate equation. In the given rate equation, x is the order of the reaction with respect to A, y is the order of the reaction with respect to B, and K is the rate constant. Also, x or y is usually a whole number integer, such as 1, 2, 3, or fractional. The sum of the exponents x and y gives the overall order of the reaction. Thus, the order of the reaction is defined as the sum of the powers of the concentration terms in the rate law. It is important to note that the order of a reaction can only be determined experimentally and not from the coefficients of the balanced equation. For any reaction, the reaction rate with respect to the reactants is determined by varying the concentration of any one of the reactants, keeping the concentration of other reactants constant. Let us look at a reaction to understand this better. Consider the reaction of acetone and bromine. Using the data in the table given here, it is possible to calculate the order of the reaction with respect to both bromine and acetone. Let us see how the rate of reaction changes with a change in the concentration of either bromine or acetone. From experiments 1 and 2, it is obvious that there is no change in the rate with a change in the concentration of bromine. For experiments 1 and 3, it is obvious that the rate is doubled as the concentration of acetone is doubled. That is, the rate depends on one concentration term with respect to acetone, while it doesn't depend on the concentration of bromine. Thus, the order of the reaction gives the mathematical relation between the reaction rate and the reactant concentration. If X is equal to 0, then it is a zero-order reaction with respect to reactant A. Similarly, if X is equal to 1, then it is a first-order reaction with respect to reactant A, and so on. Similarly, if Y is equal to 0, then it is a zero-order reaction with respect to reactant B. Also, if Y is equal to 1, then it is a first-order reaction with respect to reactant B, and so on. Thus, the sum of the exponents, X and Y, gives the overall order of the reaction. Let us write the rate equations for all the three experiments. For experiment 1, rate 1 is equal to K multiplied by 0.1 to the power Y multiplied by 0.1 to the power X. Let this be equation 1. For experiment 2, rate 2 is equal to K multiplied by 0.2 to the power Y multiplied by 0.1 to the power X. Let this be equation 2. For experiment 3, rate 3 is equal to K multiplied by 0.1 to the power Y multiplied by 0.2 to the power X. Let this be equation 3. Dividing equation 2 by 1, we get rate 2 by rate 1 is equal to K multiplied by the concentration of bromine in experiment 2 to the power Y multiplied by the concentration of acetone to the power X, divided by K multiplied by the concentration of bromine in experiment 1 to the power Y multiplied by the concentration of acetone in experiment 1 to the power X. On solving for Y, we get Y is equal to 0. Therefore, the order of the reaction with respect to bromine is 0. Similarly, we can calculate the value of X by dividing equation 3 by 1. We get X as 1, which gives the order of the reaction with respect to acetone as 1. The overall order of the reaction is therefore 1 plus 0, which is 1. We can calculate the value of K by substituting Y and X in any one of the three equations as shown. Therefore, we get the value of K as 1.64 multiplied by 10 raised to the power of minus 4 per second. The units of K depend on the overall order of the reaction. If we rearrange the rate equation for K in a generic reaction, we get K is equal to rate divided by the concentration of A to the power X multiplied by the concentration of B to the power Y. Representing this equation in terms of the units of concentration and rate, we get the unit of K as rate of the reaction divided by concentration to the power Y plus X, where Y plus X is the overall order of the reaction. The unit for concentration in the SI system is mole per liter. If Y plus X is 0, then we get the unit of K in the SI system as mole per liter per second. If the overall order of the reaction is 1, then we get the unit of K as per second. If the overall order of the reaction is 2, then we get the unit of K as liter per mole per second. Let's now understand the concept of molecularity of a reaction. A balanced chemical reaction doesn't explain the mechanism of the reaction. That is, it doesn't explain how the reaction takes place. A reaction may take place in a single step, called an elementary reaction, or in multiple steps, called a complex reaction. Each step in a complex reaction is called an elementary reaction. The sequential representation of all the elementary reactions in an overall reaction is called the mechanism of the reaction. The number of reacting species, such as molecules, atoms, or ions, of an elementary reaction, which collide with each other to bring about a chemical reaction, that is, to form a product or products, is called the molecularity of that reaction. Molecularity of a reaction is the property that helps us understand the mechanism of a reaction. A reaction in which only one molecule takes part is known as a unimolecular reaction. For example, the decomposition of ammonium nitrite. Bimolecular reactions involve two molecules. For example, the decomposition of nitrogen dioxide. Trimolecular reactions involve three molecules. For example, the combustion of nitric oxide. Why are the reactions involving more than three molecules very rare? Now let us understand how the collision theory explains the reactions which involve more than three molecules. Collision theory states that as the number of reacting species or molecules increases, the probability of simultaneous collision of reacting molecules decreases. Therefore, the possibility of simultaneous collisions between four molecules is much less than the possibility of simultaneous collisions between three molecules. Hence, reactions involving more than three molecules are very rare. Therefore, the molecularity of a reaction cannot be more than 3. Reactions involving more than 3 molecules take place in several steps, and such reactions are called complex reactions. Note that the molecularity of a reaction that takes place in a single step is equal to the total number of reactant molecules involved in the balanced chemical reaction. Let us now move on to the mechanism of a complex reaction involving more than 3 molecules. Consider the reaction of hydrogen bromide with oxygen. Here, 4 molecules of hydrogen bromide react with 1 molecule of oxygen. These molecules must collide simultaneously to react, but it is highly unlikely that 5 molecules would collide at the same time. Therefore, this reaction takes place in several steps, as shown here. You can clearly see that each step involves two molecules. That is, the reaction is bimolecular. Hence, when a reaction involves more than one step, its molecularity depends on the elementary steps. From this, we can conclude that complex reactions involving more than 3 molecules generally occur in more than one step. When a reaction involves more than one step, the elementary step that can proceed no faster than any other step is called the slowest step. The slowest step of the reaction is therefore called the rate-determining step. This concept can be understood better by drawing an analogy with the preparation of a cake. The 3 major steps involved are preparing the dough, baking, icing. You can make dough for 50 cakes. However, only 20 cakes can be baked at a time. Hence, the number of cakes on which you can put icing will depend upon the second step, baking. Therefore, baking is the rate-determining step here. Let's now go back to the reaction of hydrogen bromide with oxygen. In this example, steps 2, 3, and 4 are very fast and take less than a minute. However, step 1 can take up to a year. Therefore, step 1 is the rate-determining step for this reaction. For this step, the order and molecularity of the reaction are the same, 2. Thus, for a complex reaction, the order is given by the slowest step, and in general, the molecularity and order for the slowest step always remain the same. Consider a simple reaction in which reactant A gives product B. Using the differential rate equation and rate law, we can write the rate of the reaction in terms of the rate of disappearance of reactant A as minus dA by dt equal to K into concentration of A to the power n, where n is the order of the reaction with respect to A. If the order of the reaction is 0, that is, if the rate of reaction doesn't depend on the concentration of the reactant, then n is equal to 0. Substituting n by 0 in the differential rate equation, we get minus dA by dt is equal to K, or dA is equal to minus K into dt. On integrating both the sides, we get concentration of A is equal to minus Kt plus C, where C is the constant of integration. Let this be equation 1. Let the initial concentration of reactant A be A0 at time t is equal to 0. Substituting the value of A0 at time t is equal to 0 in equation 1, we get C is equal to A0. Substituting this value of C in equation 1, we get concentration of A is equal to minus K into T plus concentration of A0. Let this be equation 2. If we plot this equation on the concentration of A versus time graph, we get a straight line with the y-intercept as the concentration of A0 and slope minus K. We can calculate the value of K by rearranging equation 2. Therefore, K is equal to A0 minus A divided by T. Now let us look at certain examples of zero-order reactions. In general, photochemical reactions, such as the formation of hydrogen chloride, and photosynthesis are zero-order reactions. Certain enzymatic reactions and the decomposition of gaseous ammonia in the presence of platinum catalyst at high pressure, and the thermal decomposition of hydrogen iodide on a gold surface are also examples of zero-order reactions. Let us now consider a first-order reaction. The reaction in which the rate of reaction is proportional to the first power of the concentration of the reactant is called a first-order reaction. Hence, in a first-order reaction, N is equal to 1. Substituting N is equal to 1 in the differential rate equation, we get minus dA by dt is equal to K multiplied by concentration of A, or dA by concentration of A is equal to minus K into dt. Integrating both the sides, we get log concentration of A to the base E is equal to minus K multiplied by T plus C, where C is the constant of integration. Let this be equation 3. Let the concentration of reactant A be A0 at time t is equal to 0. Substituting the value of A0 at time t is equal to 0 in equation 3, we get C is equal to log concentration of A0 to the base E. Substituting this value of C in equation 3, we get log concentration of A to the base E is equal to minus K multiplied by T plus log concentration of A0 to the base E. Let this be equation 4. On rearranging this equation, we get K is equal to 1 divided by T log concentration of A0 divided by concentration of A to the base E. Since log to the base E is equal to 2.303 log to the base 10, this equation can also be written as K is equal to 2.303 divided by T multiplied by log concentration of A0 divided by concentration of A. This equation can be further rearranged as log concentration of A0 divided by concentration of A is equal to K multiplied by T divided by 2.303. Let this be equation 5. If the concentration of A is A1 at time t1, then we can represent equation 4 as log concentration of A1 to the base E equal to minus K multiplied by T1 plus log concentration of A0 to the base E. Similarly, if the concentration of A is A2 at time t2, we can represent equation 4 as log concentration of A2 to the base E is equal to minus K into T2 plus log concentration of A0 to the base E. We can also represent equation 4 as log concentration of A to the base E minus log concentration of A0 to the base E is equal to minus K multiplied by T, or log concentration of A divided by concentration of A0 to the base E equal to minus K into T. Taking antilog on both the sides, we get concentration of A is equal to concentration of A0 into E to the power minus KT. Let this be equation 6. If we plot equation 4 on graph, then we get a straight line with the y-intercept as log initial concentration of A0 to the base E and slope as minus K. If we plot equation 5 on a graph, we get the graph as shown here. Half-life period of a reaction is defined as the time taken for the concentration of a reactant to reduce to 1/2 of its initial concentration. Let's consider a simple reaction. If this reaction is of zero order, then the concentration of A is given by A is equal to minus K multiplied by T plus concentration of A0. Let T1/2 be the time in which the concentration of reactant A reduces to 1/2, which is equal to concentration of A0 by 2. Substituting the value of concentration of A and T in the given equation, we get concentration of A0 by 2 is equal to minus K multiplied by T1/2 plus A0. Calculating for T1/2, we get T1/2 is equal to A0 by 2K. From this equation, we can conclude that the half-life period for a zero-order reaction is directly proportional to the initial concentration of the reactants. Let us now calculate the value of T1/2 for a first-order reaction. For a first-order reaction, the half-life period is directly calculated from the rate constant K, given by K equal to 2.303 divided by T multiplied by log concentration of A0 divided by concentration of A. Let T1/2 be the time in which the concentration of reactant A reduces to 1/2, which is equal to concentration of A0 by 2. Substituting the value of concentration of A and T in the given equation, we get K equal to 2.303 divided by T1/2 multiplied by log concentration of A0 divided by concentration of A0 by 2. On rearranging the equation, we get T1/2 is equal to 2.303 multiplied by 0.301 divided by K. On solving, we get T1/2 is equal to 0.693 divided by K. From this equation, we can conclude that the half-life period for a first-order reaction is independent of the initial concentration of the reactant. Consider a simple reaction in which reactant A gives product B. Using the differential rate equation and rate law, we can write the rate of the reaction in terms of the rate of disappearance of reactant A as minus dA by dt equal to K into concentration of A to the power n, where n is the order of the reaction with respect to A. If the order of the reaction is 0, that is, if the rate of reaction doesn't depend on the concentration of the reactant, then n is equal to 0. Substituting n by 0 in the differential rate equation, we get minus dA by dt is equal to K, or dA is equal to minus K into dt. On integrating both the sides, we get concentration of A is equal to minus Kt plus C, where C is the constant of integration. Let this be equation 1. Let the initial concentration of reactant A be A0 at time t is equal to 0. Substituting the value of A0 at time t is equal to 0 in equation 1, we get C is equal to A0. Substituting this value of C in equation 1, we get concentration of A is equal to minus K into T plus concentration of A0. Let this be equation 2. If we plot this equation on the concentration of A versus time graph, we get a straight line with the y-intercept as the concentration of A0 and slope minus k. We can calculate the value of k by rearranging equation 2. Therefore, k is equal to A0 minus A divided by T. Now let us look at certain examples of zero-order reactions. In general, photochemical reactions such as the formation of hydrogen chloride and photosynthesis are zero-order reactions. Certain enzymatic reactions and the decomposition of gaseous ammonia in the presence of platinum catalyst at high pressure and the thermal decomposition of hydrogen iodide on a gold surface are also examples of zero-order reactions. Let us now consider a first-order reaction. The reaction in which the rate of reaction is proportional to the first power of the concentration of the reactant is called a first-order reaction. Hence, in a first-order reaction, N is equal to 1. Substituting N is equal to 1 in the differential rate equation, we get minus dA by dt is equal to K multiplied by concentration of A, or dA by concentration of A is equal to minus K into dt. Integrating both the sides, we get log concentration of A to the base E is equal to minus K multiplied by T plus C, where C is the constant of integration. Let this be equation 3. Let the concentration of reactant A be A0 at time t is equal to 0. Substituting the value of A0 at time t is equal to 0 in equation 3, we get C is equal to log concentration of A0 to the base E. Substituting this value of C in equation 3, we get log concentration of A to the base E is equal to minus K multiplied by T plus log concentration of A0 to the base E. Let this be equation 4. On rearranging this equation, we get K is equal to 1 divided by T log concentration of A0 divided by concentration of A to the base E. Since log to the base E is equal to 2.303 log to the base 10, this equation can also be written as K is equal to 2.303 divided by T multiplied by log concentration of A0 divided by concentration of A. This equation can be further rearranged as log concentration of A0 divided by concentration of A is equal to K multiplied by T divided by 2.303. Let this be equation 5. If the concentration of A is A1 at time t1, then we can represent equation 4 as log concentration of A1 to the base E equal to minus K multiplied by T1 plus log concentration of A0 to the base E. Similarly, if the concentration of A is A2 at time T2, we can represent equation 4 as log concentration of A2 to the base E is equal to minus K into T2 plus log concentration of A0 to the base E. We can also represent equation 4 as log concentration of A to the base E minus log concentration of A0 to the base E is equal to minus K multiplied by T, or log concentration of A divided by concentration of A0 to the base E equal to minus K into T. Taking antilog on both the sides, we get concentration of A is equal to concentration of A0 into E to the power minus KT. Let this be equation 6. If we plot equation 4 on graph, then we get a straight line with the y-intercept as log initial concentration of A0 to the base E and slope as minus k. If we plot equation 5 on a graph, we get the graph as shown here. You know that for a first-order reaction, the sum of the powers of the concentration terms in the rate law expression is equal to 1. The decomposition of nitrogen pentoxide and nitrous oxide are examples of first-order reactions. Let us now study pseudo-first-order reactions in detail. Consider a simple reaction A plus B gives rise to C, in which reactant B is taken in excess. The rate law equation for this elementary reaction can be written as rate is equal to rate constant K multiplied by concentration of A multiplied by concentration of B. Let this be equation 1. During the course of the reaction, the concentration of reactant B remains practically constant. In other words, the rate of the reaction depends only on the concentration of A. Hence, K multiplied by concentration of B can be replaced by another new rate constant, K dash. As a consequence, equation 1 can be simplified and can be written as rate is equal to rate constant K dash multiplied by concentration of A. A chemical reaction in which one of the reactants is present in excess and shows an order different from that of the expected order is called a pseudo-order reaction. The reaction is bimolecular, but still the rate of the reaction depends only on one concentration term. Hence, the reaction is called a pseudo-first-order reaction. Acid-catalyzed hydrolysis of methyl acetate in aqueous solution and hydrolysis of sucrose are examples of pseudo-first-order reactions. Let us now understand pseudo-first-order reactions better by considering the acid-catalyzed hydrolysis of methyl acetate in an aqueous solution. Methyl acetate undergoes acidic hydrolysis to form acetic acid and methyl alcohol, as represented by the equation here. The rate equation for this reaction is rate constant K multiplied by concentration of methyl acetate multiplied by concentration of water. Let this be equation 2. Let the initial concentration of methyl acetate be X moles per liter, while that of water be Y moles per liter at time t is equal to 0. After hydrolysis, let the concentration of both acetic acid and methyl alcohol be X moles per liter each, while that of water be Y minus X moles per liter, where X is very, very small as compared to Y. You can see from the data that the concentration of water is not altered much during the course of the reaction. Hence, in equation 2, the concentration of water, which practically remains constant, is multiplied by rate constant K to obtain a new rate constant K dash. As a consequence, equation 2 can be simplified and written as rate is equal to new rate constant K dash multiplied by concentration of methyl acetate. The acid-catalyzed hydrolysis of methyl acetate in an aqueous solution is expected to be a second-order reaction. However, experimentally, it is found to be first order. Hence, it is a pseudo-first order reaction. It is also called a pseudo-unimolecular reaction because even though the molecularity of the reaction is 2, its order is 1. Now, try to write the rate equation for the hydrolysis of sucrose and account for the fact that it is a pseudo-first order reaction. You know that sucrose, on hydrolysis in the presence of a dilute mineral acid, gives glucose and fructose. Excessive water is used for the reaction, and hence, the concentration of water practically remains constant. As a result, the rate equation can be written as rate is equal to new rate constant K dash multiplied by concentration of sucrose. Since the rate of reaction depends only on one concentration term, it is a pseudo-first order reaction. Let us now solve a numerical problem. Here is the data obtained on hydrolysis of methyl acetate at 298 Kelvin in 0.25 normal hydrochloric acid. Establish that it is a pseudo-first order reaction. Also calculate the half-life period for the reaction. In the first step, write the integrated rate equation for the first order reaction as shown here. Next, calculate the initial concentration and the concentration of the ester, that is, methyl acetate, at the given intervals of time by using the given data. The volume of alkali used for total change from T is equal to 0 to T is equal to infinity gives the initial concentration of the ester. Hence, the initial concentration of methyl acetate is 47.15 minus 24.36, which is equal to 22.79 milliliter. Similarly, the concentration of methyl acetate at 4500 seconds is 17.83 milliliter. And at 7140 seconds is 15.43 milliliter. Now substitute the values of A minus X and T in rate equation. On solving, we get the values of K fairly constant at the two different intervals of time. Hence, the reaction is of a pseudo-first order. In the next step, write the equation to calculate the half-life period. Substitute the value of K in the equation. On solving, we get T half as 12,692 seconds. We know that the rate of a reaction depends on the concentration of its reactants or on the pressure in case of gaseous reactants. Along with concentration or pressure, temperature also has a major effect on the rate of a reaction. It has been observed that generally rate of reaction increases with an increase in temperature. Also, it has been found that an increase of 10 degrees Celsius in temperature doubles the reaction rate. The dependence of the rate of a chemical reaction on temperature can be explained using the Arrhenius equation. The Arrhenius equation gives the relationship between the rate constant K of a reaction and the absolute temperature T. It is defined as K is equal to A multiplied by e to the power minus EA divided by RT, where K is the rate constant A is the frequency factor, which is a constant specific to a particular reaction. EA is the activation energy. R is the gas constant. And T is the absolute temperature. To understand this better, let us consider the reaction between chlorine nitrite and nitric oxide. In this reaction, a chlorine atom is transferred from one molecule of chlorine nitrite to a molecule of nitric oxide. According to the collision theory, in order for the reaction to occur, the nitrogen atom in NO must collide with the chlorine atom in ClNO2 with sufficient energy and the correct orientation. Before chlorine nitrite and nitric oxide are converted into products, during which existing bonds break and new bonds are formed, they go through a highly unstable intermediate or transition state. If we plot the potential energy of the molecules versus the reaction coordinate, we get the curve shown here. The peak of the curve is the transition or the intermediate state, which is also known as activated complex. The energy required by the reactant molecules to reach this transition state is known as activation energy, EA. In other words, this is the minimum energy required to cause a reaction. Even though the overall delta G of the reaction may be negative, the reactant molecules still need to go through the transition state in order to react. It is important to note that according to the collision theory, only a small fraction of the collisions produce a reaction. These colliding molecules must collide with the proper orientation with sufficient energy, called threshold energy, which is the energy possessed by reacting species plus activation energy. Hence, not all molecules have enough activation energy to take part in a reaction. If we plot the fraction of molecules with the given kinetic energy, we get the Boltzmann-Maxwell distribution curve shown here. Only those fractions of molecules on the right-hand side of the activation energy take part in the reaction. As the temperature of the system increases, the peak of the curve moves to a higher energy value, and the curve broadens out to the right, such that there are a greater number of molecules with much higher energy. As the number of molecules with higher kinetic energy increases, the number of molecules that carry energy greater than the activation energy also increases. Thus, the rate of reaction increases with temperature. In the Arrhenius equation, the factor e to the power minus EA by RT corresponds to the fraction of molecules that have kinetic energy greater than EA. Taking natural logarithm on both the sides of the Arrhenius equation, we get log to the base E multiplied by K is equal to minus EA by RT plus log to the base E multiplied by A. Let this be equation 1. If we plot log to the base E multiplied by K versus 1 by T on a graph, we get a straight line with slope minus EA by R, and the y-intercept as log to the base E multiplied by A. From the graph, we can see that as the temperature increases, the rate constant increases exponentially, and the activation energy decreases. As a result, the rate of reaction increases. As log to the base E is equal to 2.303 log to the base 10, Equation 1 can also be written as 2.303 multiplied by log K is equal to minus EA by RT plus 2.303 log A. On dividing this equation by 2.303 on both the sides, we get log K is equal to minus EA divided by 2.303 RT plus log A. Let this be equation 2. At temperature T1 and T2, equation 2 becomes log K1 is equal to minus EA divided by 2.303 RT1 plus log A. And we get log K2 is equal to minus EA divided by 2.303 RT2 plus log A. Let these equations be 2A and 2B respectively. On subtracting 2B from 2A, we get log K2 minus log K1 is equal to EA divided by 2.303 RT1 minus EA divided by 2.303 RT2, or log K2 divided by K1 is equal to EA divided by 2.303 R multiplied by 1 by T1 minus 1 by T2. Thus, the Arrhenius equation can be used to calculate the activation energy at different temperatures if the experimental values of the rate constants are known. Now let us solve a numerical problem. The rate constants of a reaction at 823 Kelvin and 898 Kelvin are 1.1 liters per mole and 6.4 liters per mole respectively. Calculate the energy of activation. The first step involves writing the given values of T1, T2, K1 and K2 respectively, and the value of R in joules per Kelvin per mole as shown. The second step involves writing the Arrhenius equation at two different temperatures as shown. The third step involves substituting all the given values in the equation. On substituting and solving, we get EA is equal to 1.4 multiplied by 10 to the power 5 joules per mole. We know that the rate of a reaction depends on the concentration of its reactants and the temperature. Along with the concentration and temperature, a catalyst also has a major effect on the rate of a reaction. A catalyst is defined as a substance that alters the rate of a reaction without itself undergoing any permanent chemical change. A catalyst thus can enhance or retard the rate of a reaction. A catalyst that enhances the rate of a reaction is called a positive catalyst, while a catalyst that retards the rate of a reaction is called a negative catalyst. Let us now discuss the characteristics of positive catalysts and their effect on the rate of a reaction. A positive catalyst increases the rate of a chemical reaction, is not consumed by the reaction, does not change the equilibrium constant for the reaction. That is, it shortens the time required to establish equilibrium, but doesn't affect the final position of the equilibrium. Also, a small quantity of the catalyst can catalyze a large quantity of reactants, since it is not consumed during the reaction and can be used again and again. You will understand this better with an example. The hydrogenation of ethene in the presence of nickel yields ethane. In this reaction, nickel acts as a catalyst. Catalysts increase the rate of reactions by providing a new pathway or mechanism that has a lower activation energy, as shown in the diagram here. A larger proportion of the collisions that occur between the reactants now have enough energy to overcome the activation energy for the reaction. Thus, a large number of collisions become effective. As a result, the rate of the reaction increases. Let us see how nickel acts as a catalyst in this reaction. Molecules of hydrogen first get absorbed on the surface of nickel by partial chemical bonds. The greater the surface area of the catalyst, the greater is the rate of the reaction. As a result, the bond between two hydrogen atoms of a hydrogen molecule gets weakened and breaks to form hydrogen atoms. These hydrogen atoms are attached to the surface of nickel by chemical bonds. In the next step, a highly energetic activated complex is said to be formed when these hydrogen atoms attach to ethene molecules by partial chemical bonds. The highly unstable activated complex further dissociates to form molecules of ethane and the free catalyst. Thus, a catalyst increases the rate of a reaction. Now let us arrive at the modified Arrhenius equation on the basis of the collision theory of chemical reactions. The collision theory was proposed individually by Max Strauss in 1916 and William Lewis in 1918. It explains how chemical reactions occur. According to this theory, chemical reactions occur when the hard, spherical molecules of reactants collide with each other. Also, the reactant particles must collide not only with sufficient energy, but also with the correct orientation. Such collisions are referred to as effective collisions. These collisions lead to the formation of the product. To understand this better, consider the collisions with sufficient energy with different orientations between ethyl bromide and hydroxide ion. The collisions in case of B with proper orientation result in the formation of the product ethyl alcohol. The rate constant for a simple biomolecular reaction, as predicted by the collision theory, is K is equal to ZAB multiplied by e to the power minus EA by RT, where ZAB is the collision frequency of reactants A and B, and e to the power minus EA by RT is the fraction of the molecules with activation energy greater than EA. The Z in this equation can be compared to the factor A in the Arrhenius equation. Since all the collisions do not lead to the formation of products, another factor called steric factor, P, is introduced in the collision theory to account for effective collisions. P refers to the collisions between molecules with the proper orientation. Taking the steric factor into consideration, the Arrhenius equation can be modified to K is equal to P multiplied by ZAB multiplied by e to the power minus EA by RT. Thus, in the collision theory, the activation energy and proper orientation of the molecules together determine the criteria for an effective collision, and, therefore, the rate of a chemical reaction.